Hi, everyone, and welcome to week 9 of Introduction to Logic. The topic for today is using the natural deduction proof method to prove that logical truths are logical truths. What will look a little strange about the proofs we're going to do this week is that they have no premises. And if you think about it, this makes sense. A logical truth is a necessarily true statement, a statement that can't be false. So it will be true no matter what the premises are. So you don't need any premises at all to prove that logical truths are logical truths with the proof method. Let's go ahead and dive in. To prove that logical truths are logical truths, in other words, to prove that they're necessarily true, there are two options. You can either use conditional proof or indirect proof or some combination thereof. And we're going to dive right into examples so you can see how this works. I want to remind you, first of all, what a logical truth actually is. Remember, a logical truth is a necessarily true statement. So what you see on the screen here is a logical truth. If we did a truth table for this, you'd see that this is necessarily true. It's impossible for this statement to be false. In fact, I'm going to do that really quickly so you can see that this is a logical truth. So there are, let's see, three statements here, P, Q, and R. So we're going to need 8 rows. So under the first letter, I'm going to set half of these to true. On the next letter, I'm going to set half of these to false. Under Q now, 2 trues and 2 falses. This should all be reviewed from when we were doing truth tables. And again, we're not going to use truth tables this week. I'm just doing this to demonstrate that this is a logical truth before we dive in and I show you how to do this using the proof method. So under this P, 4 trues and 4 falses. Under R here, 1 true and 1 false all the way down. Okay. The negation here in front of the first P is just going to be the opposite value of P. So false, 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 true, 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 true. Then we'll do the horseshoe. We have false implies true. That's true. False implies true is true. False implies false is true. False implies false is true. True implies true is true. True implies true is true. And true implies false is false. In the right side, the parentheses on the right, we have true implies true is true. True implies false is false. True implies true is true. True implies false is false. And the rest are going to be true all the way down because we have a false antecedent. And now just to remind everyone how this works, we're going to take the main operators inside these parentheses, and we're going to use the rule for the disjunction, the wedge right here, to evaluate the value of that disjunction. So here we have something true or something true, that will give us true. Something true or something false, that will give us true. Something true or something true, that will give us true. Something true or something false, that will give us true. Something true or something true, that will give us true. True or true is true. False or true is true. And false or true is true. And you can see here that this statement then is a logical truth. It's impossible for this statement to be false, no matter what the values of P, Q, and R are. So this is a kind of an unwieldy way to show that this statement is a logical truth or a necessary truth. You can accomplish the same thing using the natural deduction method, which I'm going to do right now. So let me erase this truth table like so. I'll just take a second here. There we go. Let me just erase this arrow while I'm at it. There we go. So what I'm going to do, you'll see here that there's no argument here. This is just a single statement. There are no premises. So what we're going to do, we're going to start a proof making an assumption, either for a conditional proof or an indirect proof, to show that this statement is necessarily true, that this statement is true. In other words, no matter what the premises were, if there were premises. So the statement here is not a conditional, it's a disjunction. The main operator is that wedge. So I'm going to start out making an assumption for an indirect proof. So I'm going to add a line 1, and I'm going to add a vertical assumption line, just like you do if you were doing an indirect proof inside an argument. And I'm going to assume the negation of what I'm trying to show here. So I'm trying to show that this statement is necessarily true, so I'm going to assume its negation. So I'm going to assume it's not the case, and I'm going to put all of this in a bracket. Not P implies Q, or P implies R, like so. And I'm going to call this AIP, Assumption for Indirect Proof. In fact, let me use a different color here to make that really clear. There we go. Okay. Now what I'm trying to do, like all indirect proofs, I'm going to try to show that this leads to a contradiction. And if I can do that, that will demonstrate that this this statement, the one we're given here in the beginning, is necessarily true. So we're going to try to derive an explicit contradiction, something like P and not P, Q and not Q. If we can do that, we will have shown that that statement is necessarily true. And if you think about this, this makes sense. If you can say, okay, we're trying to show that this statement is necessarily true, if we can show that its opposite implies a contradiction, we will have shown that statement is true with no premises whatsoever. Okay, so now I've got the negation of a disjunction inside that bracket. So I'm going to do De Morgan's rule. I'm going to get it's not the case that not P implies Q, and it's not the case that P implies R. Okay, and that's going to be line 1 by De Morgan's rule. And this is really nice because I've got a conjunction now, so I could simplify each of those two conjuncts. But I think what I'm going to do first, I'm going to take these implications inside the parentheses, and I'm going to convert them to disjunctions using the implication rule, because I have negations in front of them, and that will let me do De Morgan's rule. So let's do the first one first. We're going to have it's not the case that not P or Q. And then the rest of the statement we have to leave alone. We have to do this in two different steps. So the negation of P implies R. And that is line 2 by implication. I'm going to get rid of this double negation. So that's going to give us it's not the case that P or Q. And then the rest of the statement is going to be left alone. Negation of P implies R. That's going to follow from line 3 by double negation. On line 5, still inside the scope of this assumption line, don't forget to bring this assumption line down, because we don't know that these statements are actually true. We're starting out by making an assumption. We're assuming that the statement, given statement is false, and we're trying to show that leads to a contradiction. So you can't forget about that vertical assumption line. Also, make sure you're including that in your homework. I noticed that a couple of you in your homework for week 7 did not include that vertical assumption line. You need to include that line because that's what demonstrates that you're inside the scope of an assumption. Okay, let's get rid of this conditional inside the parentheses on the right. So we're going to leave the left side of the statement alone, negation of P or Q, and we're going to apply implication right here. So it's not the case that not P or R. And this should be review, hopefully, get from the implication rule from a couple of weeks ago. Line 4 by implication. Okay. Now, I'm going to go ahead and simplify these statements out. So on line 6, I'm going to get it's not the case that P or Q. That's going to follow from line 6 by simplification. Oops, there we go. And I'm going to do the same thing on the right side. I'm going to simplify that term out, but I have to do commutativity first to get that side on the left. So we're going to rewrite line 5 as it's not the case that not P or R, and it's not the case that P or Q. Line 5 by commutativity. Now on line 8, I can get it's not the case that not P or R on its own line by simplification. Line 7 by simplification. Oh, I realized I made a mistake right here. This is not line 6 by simplification. This is line 5 by simplification. Sorry about that. Okay, let's move on. So I see now that I've got a couple of nice, easy De Morgan's rule steps that I can do. I can get from line 6, I can get not P and not Q. So that's going to be line 6 by De Morgan's rule. And I can do the same thing. Oops. I can do the same thing on line 8. So I will get not P and not R. And that's going to follow from line 8 by De Morgan's rule. Now remember what we're trying to get. We're trying to get an explicit contradiction, something like P and not P, Q and not Q. And we're almost there. I'm going to scroll up a little bit. Notice that on lines 9 and 10, we've got a couple of conjunctions. So I could simplify each of those terms out, which means I can get not P on its own line from line 9, But I can also get not P, which is just P from line 10, and that's going to be the explicit contradiction that I can get. So on line 11, I'm going to simplify line 9 and get not P on its own line. So line 9 by simplification. And line 12, again, still inside the scope of this assumption line, I'm going to get not P. And that's going to follow from line 10 by simplification. And of course, that's just P. So I'm going to get rid of that double negation. That's going to be line 12 by double negation. Scrolling up again here. Again, don't forget that what we're trying to do. We're trying to show an explicit contradiction. We have a statement. We assumed it's opposite. We're going to try to show that its opposite leads to a contradiction. Okay. And on line 14, still inside the scope of this assumption line, I've done that. I've shown P from line 13, and I've shown not P from line 11. So let's see, that's 11 and 13 by conjunction. So now that we've got this explicit contradiction, again, it has to be a substitution instance of P and not P, or Q and not Q, anything like that. I can close off my assumption line, this horizontal line. Line 15 will be back outside the scope of the assumption line. And again, we have no premises. The line 1 of the proof was an assumption that we made, that came from no premises above. So in line 15, we've shown the negation of what we assumed. You have to be careful here, not the opposite, because you've actually shown the negation of it. So I have not, and here I have to scroll up a little bit. Sorry about this. Everything here. In a bracket, inside a bracket, we've got the negation of P implies Q. Or P implies R. Sorry about the scrolling there. Like so. All of that in a bracket, like that. And that's going to follow from line 1 through 14 by indirect proof. Everything inside the scope of this assumption line, and this should be review from last week. Now, the only thing I need to do to get that statement that we were given is get rid of that double negation. So that'll give us not P implies Q, or P implies R from line 15 by double negation, and we're done. So see what we've accomplished now. We've shown that this statement follows, but what does it follow from? It doesn't follow from anything at all. There were no premises that were given. We started out by assuming that statement was false. We've shown that assumption leads to a contradiction right here, and that means that the given statement is necessarily true. It doesn't come from any premises. It's true all by itself. Necessarily true. It's impossible for it to be false. So what we're going to do a few more of these. We're either going to use conditional proof or indirect proof, starting with no premises whatsoever, just like we did here. And if we can show that that statement is derivable using the proof method, we will have shown that those statements are necessarily true. So let's do a few more examples. Here's another logical truth. And again, all the exercises in this week's homework are logical truths. These are not arguments. These are just statements that are given that you're trying to show are necessarily true. Remember, an argument always has more than one statement. So looking at this given statement, what I see right off the bat is that the main operator is a conditional. So I'm probably going to do conditional proof. I'll assume that the antecedent of that is true. But then what I'm trying to do, inside the scope of that conditional proof, I'm trying to show that that statement in the bracket on the right side of the expression is true. But that in itself is another conditional. So I can do a second conditional proof, assuming P and R, and then just trying to show that that implies Q and R. And I can close off those conditional proof lines, and I'll be done. So let's do that. I think this will actually be a pretty straightforward one. Okay, so like we said, we're going to start with line 1. We're not going to make, there are no premises, so we're going to start right off the bat by introducing an assumption line. And we're going to do a conditional proof like we just described. We're going to assume the antecedent of this conditional, P implies Q. Let me use a different color. I always forget to do that. ACP, assumption for conditional proof. Now we said what we're trying to get is everything inside that bracket on the right. But that in itself is another conditional. So I'm going to introduce a second conditional proof sequence here on line 2, introducing a second vertical line. And I'm going to assume the antecedent of that conditional, P and R. And if I can, let me cite that. That's ACP again, assumption for conditional proof. And now if I can get the consequent of that conditional, Q and R, inside the scope of both of those conditional proof lines, I can close off my conditional proof sequences and wrap up this proof pretty easily. So on line 3, let's see if we can do that. Right off the bat, I see that on line 1, I've got a conditional P implies Q, and I know P is true from line 2, but I have to simplify that out on its own line. So let's get P on its own line from line 2 by simplification. In fact, I'm probably going to need R, given that I'm looking for Q and R here. So I'm going to go ahead and do the commutativity step to reverse the order of that conditional and simplify that R out on its own line. So line 4 will be R and P, line 2 by commutativity. So I can simplify and get R on its own line. Don't forget to bring down these two vertical assumption lines as you go. It's very easy to forget to do that. Okay, we're going to simplify R, and that's going to follow from line 4 by simplification. And now we, now we said that we can do modus ponens with line 1 and 3. So let's do that. Bring down these two vertical assumption lines. We'll get Q from line 1 and line 3 by modus ponens. This should all be pretty easy stuff. And we said we're trying to get Q and R together. Well, we have R on line 5. We have Q on line 6. All we have to do is conjoin those together. So R, not R and Q, Q and R, excuse me. Q and R from line 5 and 6 by conjunction. And now look what we've done. Inside this second conditional proof sequence, we've shown that if we assume P and R on line 2, we can get Q and R on line 7. So I'm going to close off this inner sequence, but remember that I'm still inside the scope of this outer sequence. So don't forget to bring down that vertical line when you close off your inner sequences. We've shown on line 8, still inside the scope of that outer initial vertical conditional proof sequence, that if we get P and R, if we assume that, we can get Q and R. And that's going to follow from lines 2 through 7 by conditional proof, CP. Now look what I've accomplished. I've shown that if I assume P implies Q, the antecedent of the conditional that we were given to try to prove that long statement in white there is a logical truth. If we assume the antecedent, we can derive the consequent. So we are done with that conditional proof sequence. Line 9 now is outside the scope of both of those conditional proof sequences. And we've shown that if you assume P implies Q, then you can get, inside a bracket now, P and R implies Q and R, like so. Close off the bracket there. And that's going to follow from line 1 through 8 by conditional proof. And we're done. Once you get the statement you're looking for on its own line outside the scope of the assumption lines, you're done. But again, just to really drive this point home, what's happening here is that this statement is a logical truth. It's a necessarily true statement that's impossible for it to be false, which means we can derive it from no premises whatsoever using one of these two proof methods, conditional proof or indirect proof. And in this case, we did two conditional proof sequences, one inside the other. But a fairly straightforward proof once you get started. The key here is knowing how to get started. Okay, let's do another one. So here's a logical truth. This one happens to be a biconditional. It says P is equivalent to this statement in a bracket, P and Q or not Q. And remember how we go about proving a biconditional. A biconditional is a conditional that goes both ways. So we're probably going to need to do two conditional proof sequences back to back to prove this conditional both directions. And then we can go ahead and conjoin those two conditionals together, apply the equivalence rule, and we will have shown that biconditional. So let's go ahead and dive in. I'm going to add line 1. So the first thing I'm going to do is try to prove the conditional this direction. If P, then everything in a bracket. And then we'll have to do the opposite in the separate conditional proof sequence. So we're going to assume P. That's going to be ACP, assumption for conditional proof. Then we're trying to get everything inside that bracket, inside the scope of this conditional proof sequence. We already have P, so now we need to figure out how to get Q or not Q. And if you're never sure what to do and you know you need something and you think you can derive it, You could try to get that by an indirect proof sequence. So what I'm going to do on line 2, I'm going to assume the opposite of what I'm looking for. I know I'm going to need Q or not Q, so I'm going to assume it's not the case that Q or not Q. And I'm going to cite this as AIP, assumption for indirect proof. Then if I can show that leads to a contradiction, I will know that Q or not Q is the case. So in line 3, inside the scope of both of these indented sequences, looks like I can apply De Morgan's rule to line 2. That will give me not Q and not Q. Okay, that's line 2 by De Morgan's rule. Now I could get rid of that double negation and apply commutativity, but notice here that I already have a substitution instance of Q and not Q, right? Not Q on the right is the negation of not Q on the left. So I've already achieved my goal of trying to show that, I've already achieved my goal of showing that this statement leads, this is assumption, the negation of Q or not Q leads to a contradiction. So I can close off that indirect proof sequence, and I can get on line 4 now, still inside the scope of that outer conditional proof sequence. It's not the case that my initial assumption is the case, and my initial assumption had a negation in it, so I've got a double negation here, Q or not Q, right? I've shown that my assumption is false, in other words. That's going to be lines 2 through 3 by indirect proof. Pretty straightforward. And I'm going to get rid of that double negation. So Q or not Q on line 5. Still inside the scope of that outer conditional proof sequence. So line 4 by double negation. Now I said what I'm looking for is P and Q or not Q. Well, I have P from line 1. I've got Q or not Q on line 5. I need to conjoin those together before I can end my conditional proof sequence. So P and Q or not Q from line 1 and line 5 by conjunction. And now I've proved the conditional one direction, right? If P, then I can get P and Q or not Q. So I can close off that sequence. Line 7, I will have shown if P, then in a bracket now, P and Q or not Q. That's going to follow from lines 1 through 6 by conditional proof. Now I'm not done yet. This is only half of the proof, right? To prove a biconditional, we need to prove that the conditional goes both ways, but we're half done now. Now we need to prove the other direction. We need to assume that expression in the bracket on the right, P and Q or not Q, and we need to show that we can derive P from that to get the conditional going the other direction. That's how you prove a biconditional using the equivalence rule. So on line 8, I'm going to start a new conditional proof sequence. Line 7 is outside the scope of any sequence, but on line 8, I'm starting a new one. We're going to assume everything inside that bracket, P and Q or not Q. And that's going to be ACP, assumption for conditional proof. Now we're trying to show all of that implies P, that the conditional goes the other direction, which is very easy to get because on line 8, we have P as part of a conjunction. So we can just simplify to get P on its own line. That's going to be line 8 by simplification. And we are actually done with that conditional proof sequence. We've shown that if we assume the right side of that expression that we're given to start the problem with, P and Q or not Q, we can derive P from that. So I'm done with that conditional proof sequence. Line 10 is outside the scope now. We have in a bracket, if we assume P and Q or not Q, then I can get P. And that's going to follow from lines 8 through 9 by conditional proof. Okay, we're almost done here. Look what I've accomplished so far. I'm trying to prove this biconditional, which means I have to show that if I could assume P, I can get the expression on the right side of that biconditional. And I need to do it the other way around. If I assume what's inside the bracket on the right side of that biconditional, then I can conclude P. And I've accomplished both of those things. But what I need to do now, in order to use the equivalence rule, I need to conjoin those two statements together. So I need to take the statement on line 7 and the statement on line 10 and conjoin them together, and then I can apply the equivalence rule. which means in order to do this, I'm going to have to introduce some curly braces here. So let's start with line 7. We're going to have P implies in a bracket, P and Q or not Q, and close off that. And another curly brace, line 10, square bracket, P and Q or not Q, in the bracket implies P, and in the curly brace. And that is going to follow from lines 7 and 10 by conjunction. A very lengthy line. Don't let it scare you. All we did was take the conditional that we got from that first proof sequence, the conditional that we got from the second proof sequence, conjoin them together with a dot. And finally now, because we have those two conditionals that are opposite of each other conjoined together, we can apply the equivalence rule on line 12. That'll give us P is equivalent to this expression in the bracket, P and Q or not Q. Close the bracket. And that follows from line 11 by equivalence. And we are done. So again, this is a pretty straightforward example. It ended up being a little more complicated and scary looking than you might have thought, given that very lengthy line on line 11. But really all we have to do is show that if we assume P, we can get that expression in a bracket, and vice versa. If we assume that expression in a bracket, then we can get P, apply the equivalence rule, and we're done. But again, most importantly, this is a necessarily existing truth, a logical truth. There's no way for the statement to be false, and it's derivable from no premises whatsoever using conditional proof or indirect proof or both. Okay, let's do a few more examples. It's going to be a fairly short video this time. There's really only a couple of learning points from this week. You just have to learn how to apply conditional proof and indirect proof to prove a logical truth, with no premises. And that's all we're covering this week, and the homework this week is actually fairly short as well. So think of this week as a little reprieve around midterm time. Once you master conditional proof and indirect proof, this unit for this week is actually fairly straightforward. Okay, so here we have another biconditional. We're trying to show that P implies Q on the left is logically equivalent to this expression, P implies P and Q. So we're going to use the same method as last time. We're going to have to prove a biconditional, which means we have to prove that if we assume P implies Q on the left, we can get the expression on the right. And we also have to show that if we assume the statement on the right, we can derive the statement on the left. And if we can do that, we will have shown that this is a logical truth, Okay. So we know we're going to need a couple of conditional proof sequences. Let's go ahead and do it. Line 1, we're going to start a conditional proof sequence. We're going to assume the left side of that biconditional, P implies Q. And that's going to be ACP, assumption for conditional proof. Now we're trying to show everything on the right. P implies P and Q. But notice that that in itself is another conditional. If P, then P and Q. So I'm going to do a second conditional proof sequence inside the scope of the first one to prove that conditional. So I'm going to assume P, assumption for conditional proof. Then all I have to do is show that P and Q follows from that. And this is going to be really easy to do. Once I have P, I know Q follows from lines 1 and 2. That's pretty easy. Easiest rule of all, modus ponens, lines 1 and 2. That should be complete review at this point. And on line 4, I can conjoin P and Q to get P dot Q. That's going to be line 2 and 3 by conjunction. Okay, now look what I've done. I've shown that if I assume P, I can get P dot Q inside the scope of that second conditional proof sequence. So I'm going to close that inner one off. I'm still inside the scope of the outer one. And I've shown if P, then, oops, excuse me, that's a typo. If P, then P and Q. There we go. That's going to follow from lines 2 through 4 by conditional proof. Now look what I've accomplished. I've shown that if I assume P implies Q, in other words, the left side of that biconditional, I can derive the right side of that biconditional inside this conditional proof sequence. So I'm going to close off this conditional proof sequence. Line 6 will be outside the scope of both sequences. If we assume P implies Q, then we can get P P implies P and Q. And that's going to follow from line 1 through 5 by conditional proof. So we're half done. We haven't proven the biconditional yet, but we've proven that this biconditional works in one direction. If we assume the left side, we can derive the right side. Now we need to do the same thing in reverse. So on line 7, I'm going to start a new conditional proof sequence. So start a new indented line because we closed off that initial line on line 5. Line 6 is outside the scope of both of those two conditional proof sequences. And line 7, we're going to start a new one. So add a new vertical line. We're going to assume the right side. If P, then P and Q. Okay. Same thing, got to cite it, ACP, assumption for conditional proof. And now we're trying to show the left side, P implies Q. Well, that in itself is another conditional, right? So we can do another conditional proof sequence inside of this one. If we're trying to show P implies Q, let's assume P and see if we can derive Q. So ACP, assumption for conditional proof. And again, I'm inside the scope of two conditional proof sequences now. On line 9, from line 7 and 8, it's pretty clear we can do modus ponens to get P dot Q. That's going to be line 7 and 8 by modus ponens. And remember, we're trying to derive Q. That's what we're trying to get. We started it by assuming P so we can try to get Q. Well, we're almost there. We've got P dot Q. We need to reverse the order of that to get Q on the left, Q dot P. That's going to be line 9 by commutativity. I'm going to scroll a little bit here. Okay. And now we can simplify and get Q on its own line from line 10. Still inside the scope of both of those conditional proof sequences. 10 by simplification. So look what we've done now. Inside the scope of that second conditional proof sequence, we've shown what we're looking for. P implies Q. So I'm going to close off that inner sequence. I'm still inside the scope of the outer sequence. P implies Q. And that follows from line 8 through 11 by conditional proof. Now look what I've done. I assumed on line 7 that P implies P dot Q, and I've shown that P implies Q follows from that. So I'm going to close off that conditional proof sequence. On line 13, now I've shown that the conditional goes the other way around. If I assume, if I assume the right side of that biconditional, which was P implies P and Q, then I can get P implies Q from that. And that's going to follow from line 7 through 12 by conditional proof. But I'm not done yet. I have to conjoin both of these two conditionals together, the one we got on line 6 and the one we have on line 13. And then I can apply the equivalence rule, and that's how I'll build that biconditional. So I'm going to scroll up a bit here. On line 14, I'm going to conjoin line 6 and line 13 together, which means I'm going to need some curly braces. I'm going to try to write small here. This is going to be fairly lengthy. So I'm going to get P implies Q implies in a bracket, P implies P and Q. Okay. And the one from line 13. So introduce a curly brace. Inside a bracket, P implies P and Q. All I'm doing is copying line 6 and 13. Don't forget your brackets and punctuation marks. Implies P implies Q. And end that curly brace. Now that follows from line 6 and line 13 by conjunction. So a fairly unwieldy statement here, but basically I'm just going to scroll up and remind you what we're doing. We're trying to prove that this biconditional goes both ways. If P implies Q, then what's on the right? And if what's on the right, then what's on the left? And that's what we've done here on line 14. If we've shown that P implies Q implies that expression in the bracket on the right side of that biconditional, and right here, that's what the dot is, And if we assume that expression in the bracket right here, P implies P and Q, then we can get P implies Q. So it's a fairly lengthy expression, but don't let the length scare you. Just break it down. Okay, and on line 15, finally, we can show the biconditional. So we have P implies Q is equivalent now with a triple bar to this expression in the bracket. P implies P and Q. And that's going to follow from line 14 by equivalence, and we're done. Okay, so again, just to reiterate, this statement here that we're given is a logical truth. In other words, it's necessarily true. Impossible for it to be false. That means we can derive that statement using no premises whatsoever, either by conditional proof or indirect proof. And that's what we've done. We started out with no premises. We started out trying to prove this biconditional works in both directions, which we did with two conditional proof sequences, conjoin the results together, apply the equivalence rule, and we've got our biconditional, and we're done. Okay, a few more examples. Okay, so here we have another logical truth that we're given. It's a conditional. It says if all of this in a bracket, if you have the negation of P and not Q, and you have not Q, then you can get not P. So because this is a conditional, I'm going to do a conditional proof sequence. On line 1, I'm going to assume the antecedent of this conditional. In other words, everything inside that bracket. So it's not the case. Oh, excuse me, got to start a vertical assumption line here. It's not the case that P and not Q and not Q. That's going to be ACP. And now I'm trying to prove not P. If I can do that inside the scope of that vertical assumption line, I'll close off my conditional proof sequence, make that conditional, and we're done. Okay, let's see if we can do it. Well, what I see right off the bat is that, well, if I know I'm going to need to get not P on its own line, I can probably get that inside the scope of this conditional proof sequence with another indented sequence, an indirect proof sequence. So in line 2, if I know I'm going to need not P, I'm going to introduce another vertical line and assume P is true. Okay, assumption for indirect proof. And now what I'm looking for a substitution instance of this, Q and not Q, some explicit contradiction. If I can get that, we can close off the indirect proof sequence. That'll give us our not P, and then we can close off our conditional proof sequence and get that conditional that we're given that we're trying to prove. Okay, let's do it. Well, right off the bat, I see that I can simplify line 1 to get it's not the case that P and not Q on its own line from line 1 by simplification. And then right off the bat, I see that I have the negation of a conjunction, so I'm going to do De Morgan's rule, not forgetting to bring down my two indented sequences here. That'll give me it's not the case that P or not Q. Line 3 by De Morgan's rule. Okay. I'm going to get rid of that double negation. That'll give me not P or Q. Line 4 by double negation. So I'm looking for an explicit contradiction here. I see that I have P and I see a not on line 2 and I see a not P on line 5. If I could do disjunctive syllogism, in other words, if I had a not Q, I could do disjunctive syllogism and I'd get not P on its own. Then I'd have P and not P. That would be my explicit contradiction and we'd be done. Well, I do have not Q. It's just locked up there inside of line 1. It's the right side of that conjunction. So I can do commutativity and then simplify to get that not Q on its own line, which I'm going to do right now. So again, keep bringing down these two sequences until we're done with them. So let's see, we're going to get do commutativity on line 1. We'll get not Q on the left, and it's not the case that P and not Q on the right. That'll be line 1 by commutativity. Now we can simplify to get not Q on its own line. Line 6 by simplification. Now we're well on our way to being able to do a disjunctive syllogism step, but we need to have the disjunction on line 5, the Q needs to be on the left so we can apply disjunctive syllogism correctly. So I need to do a commutativity step, which I'm going to do right here. Q or not P, just reversing the order of the disjunction on line 5. So line 5 by commutativity. Now on line 8, I've got Q or not P, still inside the scope of both of these two vertical assumption lines. So I can do disjunctive syllogism, and that will give me not P. Line 7 and 8 by disjunctive syllogism. Now we said we're trying to get an explicit contradiction, which we can get now. We have P on line 2, we have not P on line 9, so P and not P from line 2 and 9 by conjunction. So we are done with our indirect proof sequence because we succeeded in getting an explicit contradiction. We're still inside the scope of that outer conditional proof sequence. So on line 11, we can get the negation of our assumption on line 2, which is not P. And that follows now from, let's see, from line 2 through 10 by indirect proof. And I'm going to scroll a little bit here. There we go. And now look what we've done. We've shown that if we assume it's not the case that P and not Q, excuse me, and not Q, if we assume all of that, then we can get not P on its own line inside the scope of that vertical assumption line. So we're done with that vertical assumption line. Line 12 is back outside the scope. And we've shown in a bracket, if you have it's not the case that P and not Q and not Q, then you can get not P from that. And that's going to follow from line 1 through 11 by conditional proof. And just scrolling back up here for reference, we've shown that this is a logical truth. It's derivable from no premises whatsoever using a conditional proof sequence or an indirect proof sequence, which we did finally here on line 12. And we're done with that proof. Okay, let's do a few more examples. Okay, here we have another biconditional. So whenever you see a biconditional, when you're trying to prove a biconditional, you should immediately think, well, I'm going to try to prove a conditional that goes both ways, probably using two conditional proof sequences back to back. So let's do that. On line 1, I'm going to assume the left side of this biconditional, P implies that Q implies R. That's going to be ACP. And now I'm trying to prove the right side of this biconditional. Q implies that P implies R. Well, I think I can do this with a couple of indented sequences here. On line 2, if I know I'm trying to prove a conditional, Q implies something, I can assume Q, an assumption for conditional proof, and now I'm trying to prove that P implies R. Now, watch what I'm doing here. That itself is another conditional, so I'm going to start yet another conditional proof sequence. So on line 3, I'm now inside of 3 indented sequences. I'm going to assume P. And if I can get R inside all 3 of these indented lines, I can close off these conditional proof sequences, the 2 inner ones that I started, and get that Q implies that P implies R. So this is ACP again, another assumption for conditional proof. This should be pretty easy, I think. Just don't forget about these vertical assumption lines. Once you have P, you can get Q implies R by modus ponens from line 1 and 3. And once you have Q implies R, you can get R because we have Q on line 2. So line R, we'll get R on line 5. That's going to follow from line 2 and 4 by modus ponens. Here you have to be really careful though. Let's look at what we have on the inside assumption line. We've shown that if we assume P, we can get R. So we're done with this inner assumption line, but we're still inside the scope of these outer 2 on line 6. P implies R. That's going to follow from line 3 through 5 by conditional proof. Now we've shown inside the second assumption line, the one that starts with Q, if we assume Q, we can get P implies R. So we are done with that conditional proof sequence. If Q, then P implies R. That's going to follow from lines 2 through 6 by conditional proof. Okay, and now look what we've done. If we assume that entire expression in the bracket on the left side of the biconditional, we can get the right side of the bracket. So I'm done with this conditional proof sequence. Line 8, if we have, excuse me, there have to be a bracket there. If we have P implies that Q implies R, then we can get that Q implies that P implies R. And that is going to be line 1 through 7 by conditional proof. But I'm only half done. I've shown that the conditional works one direction. Now we need to prove it in reverse. So on line 9, I'm going to scroll down a bit here. On line 9, I'm going to start another conditional proof sequence. Starting with the right side, I'm going to assume Q implies that P implies R. Assumption for conditional proof. And now I'm trying to prove the left side. P implies that Q implies R. But we're going to do the same basic process here. Well, that's a conditional. So I'm going to start another conditional proof sequence, assuming P, ACP, assumption for conditional proof. And now I'm trying to prove Q implies R. Well, that's another conditional, right? So on line 11, I'm going to start another conditional proof sequence. So now I've got 3 going, one inside, each inside the other. We're going to assume Q, assumption for conditional proof. And now we're trying to get R on its own line inside all 3 of these vertical sequences. Okay, line 12. Again, this is going to be pretty straightforward. Once you have Q, you can get that P implies R. That's going to follow from line 9 and 11 by modus ponens. Easy rule. Line 13, still inside the scope of these 3 sequences. Now that we have P implies R, we know that P is true on line 10, so we can get R on line 13 by modus ponens from line 10 and 12 MP. Okay, we're done with this inner sequence. We've shown that if we assume Q, we can get R. Still continuing these outer sequences. So Q implies R. That's going to follow from line 11 through 13 by conditional proof. Then we're going to close this one off because we've shown that if we assume P, we can get that Q implies R. So if P, then Q implies R. That's going to follow from that second sequence, starting with P on line 10, all the way through Q implies R on line 14. So 10 through 14 by conditional proof. And now look what we've done. We've shown that if we assume the right side of that biconditional that we started with, Q implies that P implies R on line 9, we can get P implies that Q implies R, the left side of that biconditional, in other words. So I'm done with this conditional proof sequence. Line 16 is back outside the scope of both sequences. We've shown that if we assume in a bracket, Q implies that P implies R, then we can get in a bracket, P implies that Q implies R. And that is going to be line, 9 through 15 by conditional proof. Okay, we're not done. Again, we've proven the conditional goes both directions, but we haven't built our biconditional yet. So we need to take everything on line 8, everything on line 16, conjoin all of those together inside of a conjunction, and then we can apply the equivalence rule. So this is going to be a really long line on line 17. And that is, okay, I'm going to try to write small here. So line 17, I'm going to take everything from line 8 and everything from line 16 and conjoin them together. And I'm going to have to use some curly braces to do that. So line 8, we're going to have P implies that Q implies R, implies that Q implies that P implies R. I'm just copying from line 8 now, like so. And we're going to end that curly brace. And with a dot, put a big fat dot here so you can see what I'm doing. And line 16, so curly brace, square bracket, Q implies that P implies R, in the bracket. All of that implies another bracket, P implies that Q implies R in the parenthesis, in the square bracket, and a curly brace. Okay, and I'm going to cite this in pink here so you can see what I've done. That comes from line 8 and line 16 by conjunction. So this is a really massive statement, but you can see it's just the conjunction of what I have on line 8 and what I have in line 16, those two proof sequences that prove the biconditional in both directions. So I'm going to scroll up now, add line 18. Now I've proven the biconditional. I've shown that if you have P implies that Q implies R, oops, that's a pretty ugly looking bracket. I can make a cleaner one than that. There we go. That's equivalent to Q implies that P implies R. And that follows from this very long conjunction on line 17 by equivalence. And we are done. Only 18 steps. This might look a little scary, but I want you to go slowly through this part of the video if you weren't following along. Just to reiterate what I've done, I knew I had a biconditional here, right? What's on the left is equivalent to what's on the right. So like all biconditionals, I'm going to try to prove them with two conditionals that I can join together and apply the equivalence rule. If I know I need two conditionals, I know I'm going to need at least two conditional proof sequences, assuming the left side and trying to prove the right, and assuming the right and trying to prove the left. The first part of that, assuming the left and proving the right, happened right here. I'm going to use a totally different color here to indicate it. That happened here from line 1 through 8, right here. This is the first part, right there. And then the second part, assuming the right and proving the left, happened right here, which I'm going to do in totally different color again, so you can see it here, from line 9 through 16, right here, like so. That's how I prove both of those two conditionals. Then I can join the two together right here in line 17, did the equivalence rule in line 18, and we're done. Okay, so a little scary, but wasn't too bad. Okay, let's do a couple more. Okay, here we've got a conditional. It's not a biconditional. It says if that expression in the bracket, P implies Q implies R, then if you have R implies not R, you can get P. Okay, let's go ahead and do this. This is just a conditional, so I'm going to do conditional proof. Line 1, I'm going to start with a vertical assumption line. I'm going to assume the entire antecedent of this conditional, the entire expression in the bracket on the left. So P implies Q implies R. ACP. Now I'm trying to prove that bracket on the right. But if you notice, what's in the bracket on the right is itself a conditional. So I'm going to do another conditional proof sequence inside the first one to prove that conditional on the right. The antecedent of that is R implies not R. ACP. Now all I'm trying to get is P on its own line. Well, I'm going to try to do that with an indirect proof sequence. If I know I need P, I'm going to assume not P and try to show that that leads to a contradiction. So in line 3, I'm going to assume not P, AIP, assumption for indirect proof. Then if I can show that that leads to a contradiction, I can close off that indirect proof sequence. Then I can close off the conditional proof sequences. Excuse me, I forgot to add a line here. This will be add a new line. Oops, not that color either. I'm really sloppy today. Sorry about that. There we go. Change that back to yellow. Forgot to add a third line here. There we go. We're going to assume not P and try to show that that leads to a contradiction. Okay, let's see what we're working with. Line 2 says R implies not R, and by implication, that's equivalent to not R or not R. Okay, so that's line 2 by implication. And of course, when you have something or itself, you can get rid of that disjunction using the tautology rule. So that'll just give me not R. So line 4 by tautology. And that's actually really nice because that gives me the negation of the consequent of the conditional in line 1, and I can do modus tollens. So let's do that step. So line 6, still inside all 3 of these assumption lines, keep bringing them down. Let's do modus tollens. That'll give us the negation of P implies Q. And that will be line 1 and line 5 by modus tollens. Okay, line 7, keep bringing these lines down. We're not done with these 3 lines until we reach an explicit contradiction, something like P and not P or Q and not Q. Well, I'm going to apply implication to that conditional inside the parentheses. That will give me it's not the case that not P or Q. Okay, line 6 by implication. And that's nice because that'll let me do De Morgan's rule, because now in line 7, I've got the negation of a disjunction. So line 8, still continuing my 3 sequences here. We're going to end up with not P and not Q. Okay, that's going to be line 7 by De Morgan's rule. I can see what contradiction I'm going to get now. In line 3, I've got not P, and line 8, I've got not P. So on line 9, I'm going to simplify line 8 just to get not P on its own line. Okay, that'll be line 8 by simplification. Now I need to have an explicit contradiction, some statement and its negation. Well, I have not P on line 3. I've got the negation of that, not P on line 9. So I can just conjoin those together. Not P and not P. Line 3 and line 9 by conjunction. And that is an explicit contradiction. So I'm going to scroll a little bit here. So I'm going to close that off, still inside these first 2 sequences. Don't forget about those. See, we started out by assuming not P. So we are going to get not P from line 3 through 10 by indirect proof. But of course, that's just P, which is what we're looking for. Remember, we said we were trying to get P here. So line 12, still inside the scope of these sequences, we get P by double negation. So we have 11, double negation. So look what we have now. We started out by assuming R implies not R, and we got P from that. So we're done with this conditional proof sequence. Close that off. I like to use these horizontal lines to make it really clear that you're closing off that sequence. Line 13, how did we start that? When we started out, R implies not R. Oops. R implies not R. And we were able to derive P from that. And that follows from, let's see, where did R, or no, R implies not R show? Line 2 through 12 by conditional proof. And now look what we've done. We started out by assuming the left side of that bracket, P implies Q implies R on line 1. Inside that first vertical line, we were then able to get R implies not R implies P. So I am done with that conditional proof sequence. I have to remind myself what we started with here. P implies Q implies R. P implies Q implies R. And all of that implies that if you have R implies not R, then you can get P. And that's going to follow from line 1 through 13 by conditional proof, and we're done. We will have been able to derive this statement as a logical truth from no premises at all using a conditional proof sequence that started with line 1 way down here to line 13, and we were able to build that conditional that we needed. Okay, so that one was pretty straightforward, not too bad. Okay, now we have, let's see, we got the negation of a conjunction. It's not the case that P implies not P and not P implies P. So this isn't a conditional, although there are conditionals inside those parentheses. So because we don't have a conditional, I'm going to try to do this by indirect proof. So on line 1, I'm going to assume the opposite of what we have here. And here we have the negation of something inside a bracket. So I'm just going to drop that negation, drop those brackets, and I'm going to assume P implies not P, and not P implies P. Okay, that's going to be AIP, assumption for indirect proof. Now, if I can get some explicit contradiction, something like Q and not Q, or P and not P, then I can end this indirect proof sequence and just conclude that that initial assumption, what I just wrote in line 1, has to be false. So in line 2, let's see, I've got a conjunction here, so I'm going to simplify both of these conjuncts. I'm going to get P implies not P from line 1 by simplification. And remember, I have to do commutativity to simplify the term on the right. So let's apply commutativity to line 1, reverse the order of that conjunction. So not P implies P, and P implies not P. Line 1 by commutativity. Okay. Now I can simplify that the other term of the conjunction. Get not P implies P from line 3 by simplification. I think it's going to be really easy to get a contradiction from here. Let's see what we get. What I notice is that on line 2, I've got P implies not P, and by implication, that'll give me not P or not P. So that'll follow from line 2 by implication. And then by tautology, I know I can get not P now. Okay, that'll follow from line 5 by tautology. But once I have not P, notice that line 4 tells me that not P implies P. Oops. So I know I can also get P now, still inside the scope of this assumption line, from line 4 and 6 by modus ponens. 4 and 6 modus ponens. Well, there's my contradiction. I have P and I have not P. So I need to conjoin those together, P and not P. That's going to follow from line 6 and 7 by conjunction. Now that I have my explicit contradiction, I can close that off. Line 9 will just be the opposite of the negation of our initial assumption. So it's not the case that everything on line 1, P implies not P, and not P implies P. Close that bracket, and we are done. That's going to be line 1 through 8 by indirect proof. Didn't even need any secondary indirect or conditional sequences inside this first one. We were able to do it just with a single indirect proof sequence. That one was pretty straightforward. Okay. We have a fairly lengthy logical truth here. We've got a conditional. The left side of it, the antecedent, is P and Q or R. All of that implies this conditional inside the bracket on the right. Not R or Q implies that P implies Q. And even though this looks a little scary, I think if we do this kind of logically and step by step, asking at every turn what we need in order to finish up the conditional proof sequence we're about to start, this is going to fall apart really quickly. Okay, line 1. Because this statement is a conditional, I'm going to do conditional proof. I'm going to assume the antecedent. So we'll assume P and Q or R. ACP. And now we're trying to prove that bracket on what's inside the bracket on the right, the consequent of that conditional. But that in itself is another conditional. The antecedent is not R or Q. So I'm going to do another conditional proof sequence inside that one. Not R or Q. ACP. Okay. Now I'm trying to show that P implies Q. You can guess what I'm going to say about that. That's another conditional, so I can do conditional proof to get that conditional. We're going to assume the antecedent of that here inside another indented line. We're going to assume P, assumption for conditional proof, and now I'm just trying to get Q. Well, if I'm trying to get Q, I'm going to push this make this kind of as complex as I can, so you can see that actually what looks complex actually makes the proof a lot easier. If I know I'm gonna need Q, I'm gonna try to get that by indirect proof. So on line 4, I'm gonna add yet another assumption line. So I'm inside 4 assumption lines now. We know we need Q. We're going to assume not Q by AIP, indirect proof, assumption for indirect proof. And now we're trying to get an explicit contradiction. If I can do that, that will give me Q, which will give me P implies Q, which will give me not R or Q implies that P implies Q, that I can close off that outer conditional proof sequence, build that outer main operator horseshoe conditional, and we'll be done. Okay, let's see if we can do it. What I see right off the bat is that, excuse me, I now have the negation of one of the terms that's one of the disjuncts in the disjunction on line 2. So if I do commutativity on line 2, I can then do disjunctive syllogism. So let's do that. We'll get Q or not R, line 2 by commutativity. Line 6, don't forget to bring down these assumption lines. I can get not R. That's going to be from line, let's see, 4 and 5 by disjunctive syllogism. Excuse me. Now look what I have. I have not R, which is the negation of one of the disjuncts on line 1. So I could do disjunctive syllogism on that as long as I get that R on the left side of the disjunction on line 1. So I need to do commutativity on line 1, rewriting it so R is on the left. R or P and Q. Okay, line 1 by commutativity. Line 8, bring these vertical assumption lines down. All 4 of them. Well, we know we have the negation of one of these disjuncts, the one on line 7, so we can get P and Q from that. And that's going to follow now from line 6 and 7 by disjunctive syllogism. And I already see the contradiction that I'm looking for. On line 4, I have not Q. On line 8, I have P and Q. So if I can get Q on its own line, that'll be my contradiction, Q and not Q. So on line 9, I need to do commutativity to reverse the order of line 8, Q and P. Line 8 by commutativity. Line 10, still inside the scope of these 4 assumption lines, Q. That's going to follow from line 9 by simplification. Okay, I'm going to scroll up a bit here. Line 11, 4 assumption lines, 1, 2, 3, 4. Now I can get Q and not Q. And that's going to follow from line 4 and 10 by conjunction. And now I'm done with that innermost indirect proof sequence, because I've shown that if I assume not Q, I can get Q and not Q, a contradiction. So I'm going to close off this inner sequence. When you do this, be really careful. You're still inside the scope of these 3 sequences outside of it. So bring those down. Now I've shown that our assumption on line 4, not Q, is false. So I've shown not Q. That's going to follow from line 4 through 11 by indirect proof. Okay. But of course, I was looking for Q, right? I wasn't looking for not Q. So on line 13, I'm just going to apply double negation, still inside the scope of these 3 assumption lines to get Q. Let's see, and that's just line 12 by double negation. That's easy. Now remember what we were trying to do. We said we were trying to build this conditional here. P implies Q. Well, on line 3, I assumed P. On line 13 now, I've shown that that leads to Q. So I can close off that sequence right here, still inside the scope of these outer 2 sequences, to get P implies Q. Okay, that's going to follow from line 3 all the way through 13. 3 through 13 biconditional proof. Why did we do that? Well, we were trying to build this conditional here inside the brackets. So we assumed on line 2, not R or Q, and we were trying to show that P implies Q. So let's do that. We've done that. Let's close off, excuse me. Let's close off the second conditional proof sequence right here, still inside the scope of the first one we introduced. We assumed on line 2, not R or Q, and that implies that P implies Q. And that would be line 2 through 14 by conditional proof. And finally now, we've shown if we assume the left side of this conditional, the antecedent, P, N, Q, or R, inside the bracket on the left, then we can get that expression on the right. So let's close off this final conditional proof sequence. Line 16 is back outside the scope of any of the lines. What do we have here? We have P and Q or R inside of a bracket. Like so. I'm sure I got that right. Yep. Then we can get everything on line 15. So in a bracket, not R or Q implies that P implies Q. Close that bracket, and we're done. That came from line 1 through line 15 by conditional proof, and we're done. We've shown that this is a logical truth, a necessarily true statement that is true no matter what P and Q and R stand for and whether those statements are true or false. We can, in other words, we can derive this statement from no premises whatsoever using conditional proof or indirect proof, using these indented sequences. A little complicated, but that one wasn't too bad. Okay, next example. We've got P implies that Q is equivalent to P implies Q. So just talking through this one, I think it should be pretty clear how to do this. The main operator is that horseshoe, the following of P, and that's a conditional. So we're going to do a conditional proof sequence. Then we need to prove a biconditional. We need to prove that expression in the bracket. So inside that outer conditional proof sequence, we're probably going to do 2 conditional proof sequences, show that Q implies that P implies Q, and vice versa, show that P implies Q implies Q. We'll build that equivalence, then we'll close off our outermost conditional proof sequence to build this conditional. I think this is going to be pretty straightforward. It'll be a little unwieldy. I want you to follow me step by step, but I think this will be pretty straightforward. So in line 1, I'm going to assume P. ACP, assumption for conditional proof. Now I'm trying to prove everything inside that bracket on the right. But everything inside that bracket on the right is a biconditional. So I need to prove that conditional both ways. If Q, then P implies Q. And if P implies Q, then Q. So in line 2, I'm going to start another conditional proof sequence. I'm going to assume Q. And now I'm trying to show that P implies Q. Well, how can I do that? That's a conditional. So I can do another conditional proof sequence here on line 3. Assume P. ACP. And then try to get Q. Well, how can I do that? Well, I have Q, but I don't have a rule that lets me bring line down. What I can do is something like this. I can do Q or Q from tautology, line 2 by tautology. And I can do tautology again to get rid of that and just get Q on its own line. So line 4 by tautology in reverse. Okay, now I've shown that P implies Q from lines 3 through 5. So I can close off that conditional proof sequence. P implies Q. And that follows from line, let's see, 3 through 5 by conditional proof. Now I've shown that on line 2, if I assume Q, I can get P implies Q on line 6. So I'm done with that conditional proof sequence. So if Q, then P implies Q. Still inside the scope of that first conditional proof sequence we started, that outermost vertical line. That's going to be line 2 through 6, biconditional proof. But we're only half done. We needed to prove that biconditional, right? So still inside the scope of this outermost conditional proof sequence, I need to do this conditional and this biconditional the other way around. I need to start a conditional proof sequence. I'm going to assume P implies Q. Do the biconditional the other direction. Trying to get Q on its own line now. So in line 9, don't forget that I'm inside 2 sequences now. This should be really straightforward, actually. If we're trying to get Q, we have P implies Q on line 8. We can still use line 1 because we're still inside the scope of that sequence, and we haven't closed that off yet. So I can do modus ponens, and that will give me Q. From line, let's see, line 1 and 8 by modus ponens. So I've already shown that if I assume P implies Q, I can get Q. So I'm done with that conditional proof sequence, still inside the scope of this first one. I've shown that if I assume P implies Q, then I can get Q. And that's going to follow from line 8 through 9 by conditional proof. Okay, now look what I've shown. I have shown that if I assume P, way up here on line 1, I can get 2 conditionals that are the opposite of each other. Q implies P implies Q, the biconditional going one direction. And on line 10, still inside the scope of that outermost vertical assumption line, I can do it the other way around. If I assume P implies Q, then I can get Q. But in order to build that biconditional, I need to conjoin line 7 and 10 together with a dot. So on line 11, I'm going to use square brackets here. I need to conjoin Q implies that P implies Q, and P implies Q implies Q. Whatever I had in line 7, whatever I had in line 10. Conditionals that are opposite of each other. So lines 7 and 10 by conjunction. And of course, that's going to give me a biconditional because it's a conditional that goes both ways. So on line 12, don't forget about your assumption line. You're still inside the scope of this assumption line that started with line 1. We can get Q is equivalent to P implies Q. And that's going to follow from line 11 by equivalence. Right? That's what I had here inside bracket. Q implies that P implies Q is equivalent to P implies Q. So now look what I've done. I've shown that if I assume P here on line 1, the antecedent of the conditional that we're trying to prove, I can get the consequent of it, which was a biconditional. So I'm done with that conditional proof sequence. If P, then I can get Q is equivalent to P implies Q. Biconditional proof, line 1 through 12 by conditional proof, and we are done. We've shown that this is a logical truth. Okay. So this is the last example I have for you guys. I think you can see that these are not terribly complicated. What is complicated, though, is keeping track of these indented sequences inside of each other. You have to go really slowly and cautiously, making sure you close off the assumption lines as you get the piece that you need, being careful not to cite lines that are contained inside of an indented sequence that you've already closed off. And of course, you always want to look at the statement you're given. If you're trying to prove a logical truth, ask yourself, okay, is what I'm trying to prove a conditional? If so, do conditional proof. If it's not, do indirect proof. If you know you need something, like here, we knew that we needed to get P implies Q at a certain point, your mind should immediately think, okay, I know I need that P implies Q. Well, I'm going to assume P and try to get Q. And if you're absolutely stuck, if you know you need something, try to get it by indirect proof. And again, just to recap here, what we did today was basically show you a method for proving logical truths. Logical truths are necessarily true statements, statements that are impossible to be false. We can prove this using proofs with no premises whatsoever. And you do that in one of two ways, either by conditional proof or by indirect proof. or both, and you might need to use these inside of each other. Use a conditional proof sequence inside of another conditional proof sequence, use an indirect proof sequence inside of a conditional proof sequence, so on and so forth. So if any of the examples here were confusing, watch the video slowly again, do the exercises that are inside your textbook. You only have about 10 proofs to do for your homework, but you can see that these 10 proofs will take you a bit of time. I did the even ones from your textbook. You have the odd ones that you have to do. As always, let me know if you have any questions or concerns, and try to get your homework to me by Sunday at 11:59 p.m. If I don't hear from you guys, have a great week, and thanks for watching the video. I'll be back with you guys in a week. I really want to reiterate this. Chapter 7, it's very important that you have Chapter 7 down, because as we move on to Chapter 8, everything we do from here on out will take for granted that you have down pat everything we've covered inside Chapter 7. So do whatever it takes to get up to speed on anything you're not clear on in Chapter 7. Make sure you can do all the proofs, have all the rules down pat. It's okay not to have the rules memorized, because you have a list of all the rules inside the inside cover of your textbook, but make sure that you're able to at least keep up with all of these proofs. You're going to need to do the things you've done in Chapter 7 from 7.1 through 7.7, kind of with your eyes closed, in order to be able to move on to Chapter 8. So as always, let me know if you have any questions or concerns, and I will see you guys in a week. Thanks for watching. Have a great week.